want to look at a student submission that I really like because it's wrong in a lot of really good ways. This student does get to the final answer, but they get there in a really roundabout and inefficient way. It's inefficient in terms of our runtime, but it's actually really efficient in a lot of other ways. So I'm going to walk through their code, um, comment on it, and then I want to show you my version that updates on that. Um, and let me, I was going to sort of solve this real time. I was going to record the whole process so you could see me kind of iterate. And I decided instead to start uh, just as I clean up some of the mess I left behind. So I've got some code here that I'm actually not going to use. I had some stuff that I renamed. This is sort of the model for my target, and I did get there with this line. So this gives the answer. And actually what I want is I want to save that. So let's give it a name. And let me see what their setup is. Probability and num of people. So then call that probability and then num of people. It's a variable that I've already named n, which I can put in, actually, let's call it, whatever. If it works, stick with what works, and we'll build that out. So fundamentally, here is the logic that I'm looking at here. I want to be looking across these different group sizes and trying out some function that wraps up the basic logic of checking the birthday paradox. So with that, I don't need this anymore. I was looking at apply stuff. I was trying to look at the old base R way of doing this, but ultimately landed on map because I am just more comfortable with map personally. They're more or less interchangeable, but either one is sort of what you want to be doing. Now, I'm just going to keep it simple and stick with what I'm relatively fluent at, even though apply is absolutely a good thing to be familiar with. It's just I haven't needed to be familiar enough with it relative to how familiar I am with map. So I was looking at sort of thinking through this as a matrix where my number of rows represented different simulations and my columns represented different group sizes. And then I could look at, say, the average by column to figure out the probabilities, but ultimately fell away from that in favor of what I've got here, which is actually relatively simple. That did involve some iterating. It involved about, well, it looks like at least an hour of kind of banging my head against the desk. Also, while trying to wrap my head around the students' work. So let's go ahead and set this up. And actually, what I'm going to be doing here is I'm running their code through this function system.time. And that is going to tell me how long it takes their code to write. And when I ran it before, I was able to get this plot out of it, which looks about correct. But like I said, we'll get to that in a little bit. Let me just really quickly, system.time, we'll put my code also in this, and then we'll see how differently the runtime is. All right, so I've got probability, I've got num people. I don't want this. This was just kind of a mental model to sort of help me think about what I was trying to set up. So here, this student has these two wonderful nested repeat loops. I was building up to, I'm going to map a thing on a thing to match up number of people to some probability or some estimate of probability. Now what I want to do is I want to have some output. I forget what they named theirs, but I'll just call it a tibble with num of people equals num of people, and probability equals probability. Cool. So when I run mine, I'm going to get the same basic outcome, and then I'll compare the plot. So let's see, they called theirs full birthday paradox. Let's call this mapped birthday paradox. Cool. I'm not 100% sure if I get to keep the output from within system.time. I think there's a garbage collection process that might delete everything. But I do have it set so that their outcome is saved as your time, and then I'll save mine as my time. So while we're waiting for this to all run, let's take a look at what their code does. So fundamentally, they are setting up a thing for their output, and then they're running these two repetitive bits of code. So let me just make a little bit more space here. So their code boils down to this stuff. So they set up their output as a data frame where our first row says probability is 0, num people is 1. They set up a value y that's equal to 2. And that is going to show up at the bottom of this outside loop. Right, so they're repeating this. They set num shared to 0, they set x to 0, and then they do this loop. And then when that loop is done, they increment y. And if they've incremented it over 100, then they reset y and they break this loop. Now, in this case, this basically, ooh, that's clever. So what they're doing here is they go through, so they didn't need to do y equals 1, but we're going to see y show up in this loop. They didn't need to do y equals 1, so they're starting from a group size of 2, and they're going all the way up to a group size of 1. Ooh, let's see, what did we get? Your time, 238 seconds. My time, 5 seconds. So let's also see if we get the same sorts of plots. So this plot on the left was from an earlier run of your code. Here is with my code. Looks approximately the same. Oh, whoops. Nope. I take it back. It is exactly the same. Map birthday paradox. So there's with my code, yours, mine. And again, it looks about the same. So we got the same basic output. Map birthday paradox. This is what we solve for. So in my version, 1 person, 0 probability. 2, an estimated probability of 0. The literal analytic answer is something like 0.002. So it's approximately 0. But here we're only doing 100 simulations. So we're getting pretty rough estimates. And let's look at full birthday paradox. This was yours. And here it's a slightly different order. It's not as a tibble, so it doesn't print as nicely on the console, but it's still probability and num of people. You're counting up and you're getting 0, 0, 0. You're getting small numbers that increase and match the basic ground truth that we expect, some sort of an S-shaped curve that gets really close to 100% by the time we're near 100. All right, so back to the code. So this is fundamentally a while loop. While y is not 101, we increment y, we reset the value of these two variables, and then we run through this loop. Right? Now here is where the real action is. They are calculating samples. And this looks really similar to what we looked at last week, but they solved the same thing that I did with a table down here. Last week, my answer was along these lines. We run a sample of some size with replacement. We run a table on that sample, and that tells us for each of these possible values, how many people have a birthday on January 1st, how many have a birthday on February 2nd, or whatever the next item in the sample is. We ask for the maximum of that table, and we ask, is it bigger than 1? Right? So this is how I solved that basic problem, but this student, their logic, I like actually a little bit better. So let's set a y is already set to 2. So when we run this, birthday samples looks like this. They're a sample of 2 people, and it's grouped by the value 2, and they've added a count. And what that means is they're looking at each possible value and counting. And they're going to use that to figure out, is there a most popular birthday that is more common than having 1 birthday? So let me run their code a piece at a time. So there's the sample, right? They're getting 2 birthdays. They're putting that into a tibble. Whoops. Putting it into a tibble, which is automatically applying a column value called value. So that's why they're grouping by value. And what that means is now they're saying value really is birthday, right? So here's someone with a birthday of the 125th day. Here's someone with the 68th day. That would be early March. They're grouping by value, so they've got a unique group for each unique birthday in the sample. So if y is really big, right, let's manually set y to, let's set it up to 400. And then we'll rerun that code. And now we're going to have groups value. We've actually got 245 unique birthdays in this group of 400 people. Right, so given that group, or given that outcome, when we run this add count, we're getting the number for each of those birthdays. So we had 4 people with the 176th birthday, and then we arrange in descending order. So given this random sample of 400 possible birthdays, we got 4 of this day, 4 of this day, 4 of this day. But what really matters, we're simply asking the question of, are there at least 2 people in the room with the same birthday? In this case, we've got a bunch of people, right? Really very few people who don't have that. So we're going to run through actually another random sample, but I'm going to filter out to where only 1 person has that birthday. We've got 144 people who don't share a birthday with anyone. So that was 360 people in our random sample who shared a birthday, which makes it easy to understand how it can be so easy to have 4 people who share a birthday. If you have a room full of 400 people and you need to put them into groups of 4, you might just go through birthdays and group people accordingly. So they're creating this thing called birthday samples, and it is just this, right? It's some output like this. And then they set something that I would have called most common birthday, which is what's the first row of this, right? So they're slicing the first row and they're taking all the columns. And then they're asking if the value of n for common birthday. Let's go ahead and run that. So we go common birthday. We again have a data frame, or in my case, it's actually, no, it's a tibble because they manually set us at a tibble. And then we're asking what is the value of n for that. The value of n in this case is just 1. So since they don't meet this condition, num shared does not increase by 1. I don't know if I've already said this, but this is a really good way to set up the problem as I would solve this on paper. It's going to turn out not a very good way to set up the problem for R. But that's fine. Walking through the logic is really helpful here. So we've got some value of x. We're repeating and we're incrementing x. Here's where we increment x. X goes up by 1. So we started, x was 0. We go to x equals 1, x equals 2, x equals 3. And each time we repeat through this, and then we increase num shared if appropriate, right? If, whether or not that's the case, whether or not we increase num shared, we increment x1, and then we come back, we run a sample of y people, which is from the outer loop we're working through, where we increment y up after we get through this loop. And then we figure out, is there a most common birthday with more than one person having that birthday? If so, we increment num shared, and we again increment x and repeat that code again. They're essentially saying, do some stuff, then do that same stuff, then do that same stuff. But if x equals 100, then we're going to do something different. And here is where we break out of the loop. So this is the most important thing. We increment up to x equals 100, we break that inner loop, we go to the outer loop where we increment y, and then we go back to the top again, we repeat this. We say num shared is 0, x equals 0, let's do this loop, but now y equals 3. So with y equals 3, they're going to run through the simulation again, and they're going to count how many of 100 simulations have at least 2 people sharing a birthday. That's the basic logic. Now the rest is sort of administrative. So they say if x equals 100, they reset x to 0, they reset num shared to 0. And they don't need to because they do that at the start of this outer loop anyways, but it's redundancy that could reduce the chance that something bad happens. Right? So if you were to accidentally eliminate those 2 lines of code, they're still resetting them. So it's unnecessary, but it's a good thing to have. More importantly, they calculate the probability as the num shared, which is the number of times there is a shared birthday, divided by the 100 times they're simulating this. They go from 0 to 99, but that's the same as going from 1 to 100. So they get the probability, they reset some values, and then they update some stuff. They're going to create a data frame out of the birthday samples. They're going to add some counts. Data frame, birthday samples. So this will be the last simulation they did. The probability is going to be, all right. Probability is their estimated probability, right? So they're testing on y equals 2 or y equals 400, but let's say y equals 2. They find how many times there was a shared birthday divided by 100. So we got an estimated probability of 0. Along with birthday samples. Let's run that code and see what it looks like. Birthday samples, probability. Birthday samples, probability, add count. Name equals num people. Right. People, probability. Birthday select. All right, so here they're doing kind of a lot of little fiddly things, and it's kind of a little tricky to follow. But in any case, it works, right? That's kind of the most important thing. Here they reset all their variables, which is really good. So here we got, say, birthday samples. They're going to make that just the 0th row of that. So now birthday samples has the same columns, but it has no observations. Right? So they're just doing that for everything. They're resetting 0. They're tidying up after themselves after they do the most important thing, which is they R-bind. They attach their birthday select data frame onto the data frame that they're building. So ultimately, the student is able to get an estimate of these answers, but as we saw, it took 280 seconds, right? Your time, let's say, divided by 60, took them 4 minutes. My time, we'll see, took 0.08 minutes. 5 seconds, that's right. So they do all that stuff. They got a loop inside a loop, and that is the basic structure of the problem. And like I said, this is exactly how I would solve this problem on paper. And again, they're fastidious. They're tidying everything up. This is really nice. When it runs, it also resets. It resets y back to 2. It's set so that you can just start running over it again. It's really, really nice. But it's really, really slow. It's not taking advantage of sort of the basic expectations of R code, which the big one is we are going to be vectorizing stuff. And it's easier to vectorize stuff if we set up our own functions that do exactly what we want to do. So let's look at how I set this up. So I'm going to check the same group sizes as them, 1 to 100. I'm going to run the same number of simulations as them. I've got birthday sample, which we've seen stuff like this before. And all this does is it samples out of our possible birthdays some sample size, right? I put in n equals 23 by default, just so that I can do stuff like run birthday sample without putting anything in and just kind of see what happens. In this case, for a group of 23. If I run 2, I should get a lot more falses. So with that, I've got something that I can repeat. And when I want to repeat stuff, I really like to repeat stuff using map. Now, map by default returns a list. And again, we're getting into some technical stuff here. We're thinking about data types. So a list is really useful for some stuff. All of our stuff is really ultimately made out of lists in some sense. But there's lists, there's data frames, there's matrices, there's all these different things. Just think of them as collections of data. And the data is going to be things like numbers or truth values or words, right? It's going to be just some stuff. A data structure is a structure to hold some stuff, and most data structures at the end of the day are some version of a list of things, right? So a list of numbers, or in this case, what we really want is a list of logical values. So map logical, what this does is it returns a logical vector so that when I run simulate by size with a default value of 23 and 100, I get 100 simulations for a group size of 23 running birthday sample. So this is just in vector form, and this I can use to estimate the probability just by finding how many trues are there relative to how long it is. But I can do that really simply with just mean. Mean takes care of it for me. So for different simulations, I'm getting a different value. So let's try s equals 1,000. It's going to take a little bit longer, but I'm going to get a little bit more precise and a little bit closer to the true value on average. And this is what's going to let me estimate these probabilities for each of these group sizes. Now, let me dig a little bit deeper into exactly what I've got here. So simulate by size is fundamentally taking 2 inputs and returning this logical vector. And I want that because I can take that logical vector and find the average value of it to get an estimate of the probability of finding a true value in birthday sample. So for that to work, I need to be able to vary the size of the group, and I need to vary how many times I run the simulation. So the way I've got that, map by default is going to take in x and f. calls it .x.f. .x is some sort of a data thing, and .f is some sort of a function. So birthday sample is a function that I can use in a call to map. Now, in this case, what I'm going to be doing is I'm using map to run through S simulations all of the same room size, the same size of group of people to ask birthdays of. So I'm going to do a thing that I have come across so many times as I've tried to solve these sorts of problems in whatever case I'm using R for. This is called an anonymous function. And this is kind of advanced stuff. It's simple and it's not, right? You don't really need to know what exactly it's doing so much as you need to identify that this is something you will see out in the wild. So we might as well look at it, right? Don't sweat it. If this seems weird, you'll get more comfortable with it over time. So when we name a function, we've got something like birthday sample. We're assigning to that item, to birthday sample, this function. An anonymous function, we take the function, but we don't bother naming it. So all we're doing is we're getting rid of that, right? That is essentially what we're doing. Now we could have skipped this whole birthday sample thing and plugged this into simulate by size, but breaking it down one piece at a time lets us, run birthday sample on the console and kind of wrap our heads around it a little bit easier. It's going to make my life a little bit easier to run it like that. So I've got birthday sample is not an anonymous function. It is a named function. Here I am mapping over logical S. So let me show you what that is. That's just a logical vector of S items. Right? So S is 100 by default. So logical 100 gives us 100 false values that we could then update to a true. Right? So if I were to say, let's do this. I'm going to make a temporary item called T. There's T. And if I were to say T number 5 takes on a value of true, now when I look at T, there's that true. Now let's say T number 5 takes on a value of hat. T, you can see it's changed subtly. It did what I told it to do, but in order for that to work, it changed the type of vector that T is into a character vector. So when I named T to begin with, that was a logical vector. Logical as in it's all true or false. Boolean is what you'll hear me refer to it as. When I said the 5th item of T gets true, I got this result, which was still a Boolean vector. When I said it gets the value of hat, it said, sure, we can do that for you. But then it changed all these falses to characters, to something it interprets as text. So we can ask, for example, is false the same as false? And the answer is going to be, oh, true. Okay, it did that appropriately. Let's try false. There we go. So this false, it can figure out in the right context, right? Someone has built in some code in the background to make this work the way you might hope it would, but it is also easy to potentially introduce some weird problem somewhere where you accidentally change T from a logical vector to something else. Again, I'm going off a little bit on a digression here, and it's kind of some advanced stuff, so don't sweat it. But what we've got here is for map logical, I am going to be mapping over a logical vector because I want a bunch of trues and falses that when I pipe into mean, it's going to convert into numbers. Let me just show one more thing. Here's T, and let's say T5 takes on a value of 1. Now T has been converted into a numeric vector. And if I take the mean of T, I'm going to get 0.01. That's fundamentally what's going on here. We generate all these true falses. Was there a match? And then we change it into zeros and ones and take the average of that. So again, map logical. We're mapping over a bunch of zeros or a bunch of falses. This function that we're defining right here, this function takes x as an input. And what it's expecting for x is whatever we get out of here. So we look at the first of our 120 logical values, we get a value of false. We say, all right, this function, we're getting false for x. What do we do? Well, we take birthday sample for a value of n. So we ignore the x. This anonymous function setup allows us to take that input from map and do nothing at all with it, but actually instead do this function that does a thing we want to do, taking the n that we pass in when we call simulate by size. All right, let's take a step back. We are basically there for solving the problem. Exactly how we're doing it, we've got two different ways to solve it, and both are getting to the same answer. Both of them are fundamentally saying, let's simulate some size of group of people. Let's pull their birthdays, and let's see when we have two or more people who share the same birthday. And we're going to do that for 100 random simulations for the first 100 numbers from 1 to 100 to see what we can get. So, with this nested while loop, it took us a few minutes. With this, we are setting this up. We are vectorizing this. We are also setting up the code so that we can see sort of exactly what's going on. My names could maybe be better, but still, at least I'm naming stuff so you can kind of see along the way what's going on. So still about 5 seconds to run that, and I still got something just as valid. So I'm going to change this a little bit. So I'm going to check the groups from 1 to 367. I'm going to run 1,000 simulations for each. And let me again check your time, 238. So let's see if I can beat 238 seconds. So with this, again, here are the sizes I'm going to check. Here's the number of simulations. That I'm passing in here. This is really the key to the whole thing, where we take these three functions we've defined, and we use the one that encapsulates all of it. We map that over big N, which is our set of possible birthdays. So for each possible birthday, we are trying out what about n, or sorry, not each possible birthday, each possible group size from 1 to 367. For each one, we're trying that. And I want to double check. I want to eliminate this default value for S, because that kind of went faster than I expected. My time, 23 seconds. So we'll see in a second if that is legit. So our fundamental answer, what we really care about, is estimating this probability. We're going to roll that together into some outcome over here. We're going to put that into the data frame that gives us mapped birthday paradox, that gives us these numbers, 367 different rows, and then that's something that we can pass into ggplot to see what it looks like. I kind of think I was not doing the full 1,000 simulations for all of them. So I think that 23 seconds is a little bit too high. So let's try running that again. S is missing. S. Estimate by size. I think what I've got to do here is I've got to put in another anonymous function. So function X, well, let's call it function N. We're going to estimate probability by size for N, and for S equals what do we call this? Lowercase s. All right, let's try it again. This should take longer because we're doing 10 times as many simulations. So we put the answer together here. That's just some of the tidying up that we're going to have to do anyways, right? Here is our student's version of that tidying up. Mine, a little bit easier. Estimate probability by size is the thing that we are applying or that we're mapping over, that we're repeatedly doing for all these different group sizes. And this is just saying we're going to run a simulation and we're going to check to see the average outcome of those simulations. To get those simulations, we're going to simulate by size, where we're just going to map some number of times, some anonymous function that is basically just a way for us to apply birthday sample without worrying about this logical S. This is doing the same thing as saying a for loop. We're going to do this S times, but don't worry so much about how it works. Just know that it works. And when you need to, you find some example of working code and you rip it off and you fit your code in where you need to. Birthday sample is where we're doing our fundamental sample. So this is the individual unit of analysis, right? We're running some simulation with some group and asking, do we get more than one people who have any one birthday? We return a true or false. We do that S times. We do that S times and take the average number of trues out of those S times. And then we do that for all of the N possibilities from 1 to 367. And the outcome is, let's close this all up. Let's fold it all together. So you went from 4 to 57. I went from 60 to 87. So I did 27 lines, what you did in 55. So I took half as many lines, which even if that meant my code ran a little bit slower, it might be worth doing that just because it's easier to see what's going on with this. As you can see already, we've spent 38 minutes looking at this code. And it's important to look over this code, but 38 minutes is more than I necessarily want to do in class. So I'm glad I'm recording this. But all of this, right? So here you've got two loops. You repeat over Y, you repeat over X. Y is telling us the number of people in the room, so we're trying all the values from 1 to 100, or 2 to 100. And X, we're just counting from 0 to 99. We're doing 100 simulations. You're very explicitly showing what we're doing, and you've got the code only written once, which is really good. You've got it once, and then you've just got the loops structured around the code that matters. And you're updating your output, and you are getting the answer. So this is perfectly legitimate code, but it took a long time, and you only ran 100 simulations. Maybe I'm going to embarrass myself. Maybe this is going to crash my computer, and 1,000 simulations is just too much, which doesn't seem right. If I had a gaming computer, this would go faster. If you can put this onto, there are ways to make your computer handle repetitive stuff faster, like using a GPU. All right, so let's look at my time. Running 1,000 simulations, 225, compared to your time, 238. So I got basically the same amount of time, but I did 10 times as many simulations per group size, and I did 3.5 times more group sizes. So I was doing 35 times as much computation in the same amount of time by using map rather than repeat. What that means is, in this case, my probability estimates are going to be more precise than yours. So let's look at, let's say, the first 100 rows, 1 to 100, and we can compare that to your code. You can see, here's yours, here's mine. Mine's a lot smoother because I'm averaging across 1,000 simulations instead of across 100 simulations. I'm going to be much closer to the true probability in this case. Now, we could calculate the true probability, but the simulation, well, it's good for your brain. It's good for mastering repetitive tasks in R. All right, so let's close here. What have we seen? We've seen two different approaches to solve this same problem. One really clever and inefficient. One practiced, right? This is my output based on having used R for a long time and having over that time gotten better at vectorizing my approach and using map. But with that practice, all I've done is I've set up some functions and then I've mapped over one of those functions a bunch of times, and that got me the output in a way where it's pretty easy to see what's going on, right? If I had a better name here, if I name my functions better than this, I think birthday sample is not the most descriptive, but I could Control F, change that everywhere. Now that we know what it is, we're checking true or false. We're checking that a bunch of times, and we're converting that into an estimated probability. Now when we look at this, we're saying across these potential group sizes, we are checking estimate by probability for the group size for the number of simulations, and then we're just putting that together into a data frame to give us our final answer. That is easier to wrap your head around than this. We're iterating over this, we're iterating over Y, we're updating things, we're clearing things out. This is really nice, careful code, but there's so much of it that it becomes harder to keep track of. There's not so much of it that we couldn't look at this example and wrap our heads around it in less than an hour, which is why I'm so excited to see it. It's such a perfect example. Really, really like this. But in the same amount of time it took to run that code, we could have gotten a better answer that covered more possibilities by using map, which basically is taking our code and converting it into C code on the back end that's going to run much faster. We can talk a little bit about that in class if you're curious. I don't know a huge amount, but basically what it boils down to is R is a high-level language that's good for thinking in. C is a low-level language that is good for the computer. By using map, we're able to use someone else's insight into these setups, into these sorts of problems, to convert our R code into someone else's C code so that we can get our output a lot faster, but also get the setup a lot easier. All right, we'll close there.